Vanakkam. Welcome to this course on biomedical instrumentation. In the last week, we looked at several things. We looked at the electrophysiology of the eye, ERG, EOG, biofeedback, electrodermal measurements, that is galvanic skin resistance, and we looked at phonocardiogram, we looked at digital stethoscope. Then finally, we also looked at an introduction, a very basic introduction to the respiratory system. Note that this course is a course on biomedical instrumentation, and the respiratory physiology part, any physiology part for that matter, is beyond the scope of this course, but you still need to understand enough physiology to be able to design and critically evaluate medical devices and medical instrumentation. So, only that much physiology is covered. Obviously, it is not a substitute for learning in a physiology course. So, please do supplement your understanding and learning by going deeper, by reading books or by going through online courses or some other online resources to improve your understanding of the respiratory system. Why is this such a big deal? Because since COVID-19, or at least during COVID-19, there was a huge understanding of the critical need for ventilators, because there were so many people who passed away because of the lack of access to ventilators. So, in this video and in the set of upcoming videos, we will discuss ventilators, and practically the entire week I think will be consumed by ventilators. If there is still time, I will start discussing pacemakers, or it is also possible that we will not even be able to finish ventilators. The topic will go further than originally planned. In this class, we will look at an introduction to ventilators, what is the need for ventilators, artificial ventilation, history of ventilators, various types of ventilators, what are some of the critical terminology for understanding ventilator function and ventilator design, what are the equations or what is the equation that governs ventilation, operation of ventilation or ventilator operation, and classification of ventilators. So, ventilator is a medical device that provides artificial ventilation. How is natural ventilation happening? Well, natural ventilation is happening due to the contraction of the diaphragm muscle, which essentially creates a negative intrathoracic pressure of the order of 2 to 5 centimeter water. So much negative intrathoracic pressure is created by the contraction of the diaphragm. Because of this pressure gradient that is created by the diaphragm contraction, this gradient exists between the external world and the inside of the thorax and the lungs. Due to this reason, there is a natural flow of breath inside. It is actually way more complicated than that. I am oversimplifying it, obviously. Now, suppose a person is not able to breathe, maybe due to, say for example, due to anesthesia. The person is not able to breathe, they are undergoing some other procedure, their respiratory system may indeed be intact, but they may undergo some other procedure that causes a total muscle blockade, that they are not able to breathe. Well, in that case then there is a need for artificial ventilation, and then there are cases, situations, disorders of the respiratory system in which there is a need for artificial ventilation. So, ventilator is used in various conditions, including when there is a need for complete takeover by ventilator. Now, that is a situation in which for example, we discussed the general anesthesia case, when complete takeover by the ventilator is required. But then there are also cases where the patient is able to breathe but not able to breathe as well. Well, in that case, then there is a need for partial support and assist type of this. We will discuss all these cases in good detail in future slides and future videos. Essentially, your ventilator adapts to the needs of the patient. It should, but the primitive elementary ventilators do not do that. They were rather open loop, but the current present day ventilators are closed loop feedback systems that adapts to the needs of the patient. Now, what is the physics behind the operation of the respiratory system and the ventilators? Before we proceed to the physics, let us discuss the design and fabrication of a ventilator. Ventilators are programmed by trained professionals, biomedical engineers such as yourselves, who will decide and design appropriate hardware and then program using an appropriate algorithm depending on the situation. So, now there is a need to adapt to the situation. So, that means that your algorithm should account for and adjust according to the particular situation. So, along with maintaining adequate flow of oxygen, they also must account for the ratio of supplied gases. Note that air in general has 80% nitrogen. So, oxygen is what is needed by the body. How much percentage oxygen you send is also something that the system should account for and control. So, essentially the ventilator is an electromechanical device. Well, it is electrically controlled, mechanically operated or mechanical output, mechanical actuation, but electrically controlled device that can, which can artificially support breathing based on specific requirements, maybe pre-programmed parameters. The ideal ventilator is one that adapts to the situation. Depending on the situation, it might take over completely or it might provide minimal support. Now, that is the ideal ventilator that performs in the whole range of operation. Now, that is still something that is in the works. Some of you who are interested may take that up as a career, for example, as an entrepreneurial venture, for example. Now, let us go back to the physics. What is the physics behind breathing? Well, what governs lung function? Lung function itself is governed by this P1 V1 equal to P2 V2. What is this? High school science, what we learned, this is actually Boyle's law, of course, is it not? This governs lung function and lung expansion. So, pressure difference essentially leads to a filling of lungs, essentially increasing the volume. That is a simple law that governs the function of the lungs. Then, what is flow? We discussed this in the previous class, I think. Flow is comparable to current. Then, this is essentially a function of the difference in pressure. So, V equal to IR means if I, then I equal to V by R. Then this is essentially the pressure gradient divided by R, where R is the, R in the electrical case is the resistance, is the electrical resistance. In this case, it is the airway resistance. Lung compliance is the change in the volume by the change in the pressure. For a given change in pressure, by how much the volume of the lungs change. It is essentially a measure of the elasticity of the lungs. Note that this will change as a function of age, as a function of health of the lungs. So, delta V by delta P is a measure of, that is, for unit change in pressure, by how much volume the lungs can change. That is the question. Right. So, that is a measure of lung compliance, which is a measure of lung health, right. That changes as a function of age, lung health and various, depending on whether the person is having COVID or not. By the way, it also varies as a function of where you are in your pathological journey. I mean, if you are recovering, then you might have had a worse complaints, but then it might improve later on, and so on and so forth. It's a complicated topic beyond the scope of this discussion, but it's important to know these things, what is flow and what is complaints, for our future discussions. Now, this is an image that is demonstrating how a ventilator functions. So, in this case, so you have the ventilator, which is an electromechanical device. So, it is electrically controlled and mechanically pumping air. It is not merely a balloon, it is more than that, but it is pumping air. As it is pumping air, what you see at the level of alveoli, the green color indicates oxygenation and the red color indicates removal of carbon dioxide from this. And as the pressure is building, there are different, as the pressure is changing because of the function of ventilators, there are different pressures of interest for us. First is you reach, as this is happening, first is, not sure if the picture is visible, first you reach a peak here and then there is a drop that happens. This peak is called as a peak inspiratory pressure or PIP, peak inspiratory pressure, and then there is a drop, after which there is a plateau that happens. There is a plateau, okay. That plateau happens, right, and that after that plateau, then it drops. Then this plateau is called as, this second level is called as a plateau pressure, and then there is a driving pressure between these two, between the fourth one and the first plateau and the second plateau. The difference is called driving pressure, and then there is a longer plateau that is called as the positive end expiratory pressure, quite often called as PEEP, positive end expiratory pressure. In future videos and in future slides, I will often use PEEP. PEEP means what? Not peeping in. PEEP means positive end expiratory pressure. That is the pressure in which there is going to be a plateau at the end of the expiration, when carbon dioxide leaves the system. Okay. Recall how gas exchange itself happens. What is the law that governs gas exchange itself? We discussed this. That is actually diffusion, fixed law of diffusion. That is actually J is minus D times A times the concentration gradient must come into the picture, is it not? That is delta C by delta X, where delta C is the concentration gradient and delta X is the distance, where A is the surface area. Now, how does the system maximize this flow itself? Well, there are things that the system can control, and then there are things that the system cannot control. For example, something that the system controls evolutionarily, has controlled evolutionarily, is the surface area. The maximum surface area is the surface area, it's about 70 meters squared in adult lungs. That's a huge area. As an exercise, try to find out how much would be the area that is 70 meters squared. 8 meters by 8 meters, a square of 8 meters by 8 meters would be 64 meters squared. That's smaller than 70 meters squared, is it not? So, go to a playground and try to draw an 8 meter by 8 meter square and see how big that is. That much bigger than that, slightly bigger than that, is how much area your alveoli are having inside the lungs. Now, that is the beauty of the respiratory system. So, that is a huge area. So, that is one way in which the system is maximizing. What is the need for ventilators? One common situation in which the person is not having, may not have a problem with the respiratory system is to aid in surgery when the person is undergoing, say, general anesthesia or some medicine that has caused, say total muscle blockade. Well, in that case, you need to aid in surgery by providing ventilation, supporting through ventilation. But there may be cases in which ventilation might be needed because of the respiratory system disorder. Now, you need to support breathing for the patient when the person is not able to breathe on their own, and to maintain oxygen level. The person might be able to breathe, but may not be able to breathe sufficient amount of oxygen. The other thing is to remove carbon dioxide. What will happen if you do not remove carbon dioxide? There will be a buildup of carbonic acid, is it not? We discussed that in the previous week, in the previous class. That is a situation that causes respiratory acidosis, not. So, you have to not only add oxygen, you should also remove carbon dioxide, and it is absolutely critical in providing life support. So, it is a fundamental part of critical care units and intensive care units. So, the other case is a situation in which the lungs might be functioning, but you want to take some load off the lungs so that they can heal. Maybe they are injured too much. You want to give them some time to heal, so that if you can support that. So, that is supporting. Okay, from here there is such a thing called as work of breathing. What is this work of breathing? This is essentially the integral of P times dV. It is a product of pressure times the volume measured in joules per liter, for example, of oxygen breathed in. Now, the history of ventilators, right? Very starting with old systems to the present day systems. This is a 1907 system in which this is the pulmotor era. This is called as the pulmotor era. This is the situation in which a negative pressure is artificially created by putting the person inside a iron lung, right. So, this is the original Drager's pulmotor. Then in 1928, this is called as the iron lung. A lot of people used to be inside an iron lung for a long time, even as late as 5-10 years ago. There were a lot of people who were inside an iron lung. So, the advantage of these systems is that it creates a negative pressure inside. Artificially, it creates a negative pressure inside between the atmosphere and the person's thorax. By when it does that, there is a natural breathing that happens. What is the problem? Well, the problem is the patient cannot be inside this iron lung forever, all their life. That is the problem. It is not portable. It is by no way. It is essentially a complete jail for the patient. The patient will be alive, but they can do nothing else in life. So, that is the disadvantage. But the advantage is that it does not force air into the system, but creates a negative pressure such that air naturally flows in. That is how breathing itself happens. Breathing is natural, it is not forced. Right. Then 1965 onwards, you have the modern feedback control based systems, and in 2024 you have this feedback control that may probably be beginning to assist using machine learning and AI, maybe providing a tailored feedback, etc., tailored input, etc. So, ventilators can be classified using many different ways. One way is the particular use case. The first is the use case when a patient is anesthetized and they may have total muscle blockade, which means that the diaphragm cannot contract. So, we need to provide artificial ventilation. That is a known case. In this case, note that the patient may not have any respiratory problem themselves. They may have some other problem. They may be undergoing surgery for some other problem. Then the critical case are the intensive care unit ventilators, and then the use of home based ventilators, where the patient is on ventilation but at home. Note that the technological rigor and the particular design and the model and the application varies, and depending on that, the specific model, specific use will also vary. So, all of this will vary. So, this is one way in which you can classify ventilators. What are some of the important terminology to discuss ventilators? First is inspiration. Inspiration means not inspiration where you are inspired, not that inspiration. In this case, when you say inspiration, you are talking about inspiration of air, process of air entering the airway. This is called inspiration. Then you have expiration. Expiration means when air leaves the airway. Breath is essentially one complete cycle of inspiration and expiration. So, you inspire once and then expire once. Pressure controlled is a situation in which the variable, the set variable that is used to control is pressure. Volume controlled is the situation in which the set variable that is being controlled is volume, of course. MAP in this case refers to mean airway pressure. Note, previously we discussed another MAP, that is a mean arterial pressure. Okay. In this case, this is actually mean airway pressure. Then the maximum airway pressure is called as P max. We already discussed this PIP. What is PIP? PIP is peak inspiratory pressure. You have PIP and then you have PEEP. PIP is peak inspiratory pressure. PEEP is positive end expiratory pressure. These are two different things. Of course, these are two different things. PIP is much higher than PEEP. Then tidal volume, we discussed this. This is the volume of gas that is delivered on an average with every breath. The minute volume is the amount of volume, is the amount of gas, is the volume of gas that is delivered per minute. That is a minute volume. NIV means what? NIV means non-invasive ventilation. NI means non-invasive, V means ventilation, non-invasive ventilation. The pressure that is delivered during inspiration is called as inspiratory pressure. Compliance, I already mentioned this, I already discussed what this is. This is the change in the volume per unit change in pressure. This is a fundamental measure. It plays a critical role in predicting the capacity of lungs to expand and essentially is a critical measure of lung health. Airway resistance, this is essentially the resistance to flow of air in the trachea. Inspiratory flow is the flow of gas that is delivered to the patient during the inspiratory phase. Expiratory phase is the flow rate of gas that is expired by the patient. Respiratory rate is the number of breaths that is taken by the patient, both including both the mandatory ones that are supplied by the ventilator and the ones that are taken by the patient per minute. Inspiratory time is the time that is taken for inspiration. Expiratory time is the time duration that is taken for expiration. I by E ratio is not the ration, but rather ratio of inspiration to the expiration time, I by E ratio. End tidal carbon dioxide level is called as EtCO2. I already mentioned that the percentage of oxygen that is supplied is called as FiO2, which is functional inspiratory oxygen in percentage or fractional inspiratory oxygen, the amount of oxygen that is there in the gas that is delivered to the lungs. Trigger is the particular variable or parameter that is mechanism that is used to start the ventilation to the patient. Sometimes it may be the patient is breathing, but there might be a time when the patient might need ventilation. Inspiratory window is the window during which inspiratory triggers are detected. Expiratory window is the window during which expiratory triggers are detected. The mode of operation of a ventilator is called as ventilation mode. We will discuss these modes later. Maneuver is a set of all procedures that is done during ventilation that needs some additional settings. So, you need to do some specific maneuvers. We will discuss these maneuvers also in detail later. Then there are flow triggers, triggers that are based on inspiration or expiration, expiratory flow. Then there are pressure triggers, triggers that are based on the particular level of pressure or based on inspiratory pressure in assist modes. And in some cases, time trigger, there is a particular time window that is used to detect triggers and then to follow up with mandatory ventilation. So, these are the various triggers that are there, various terms that are there. What is the equation that governs ventilator operation? this is the equation. The ventilator operation is governed by this equation, which is essentially PTR plus P muzzle, the pressure of the trans-respiratory difference plus the muzzle difference or the ventilator muzzle difference. This is a compensatory pressure that is essentially replacing delta P mus. And what is this delta P mus? We saw this. This is the pressure that is created by the contraction of the diaphragm. This is the pressure. This is like so the diaphragm is creating this difference. This is a compensatory pressure that is going to replace the function of the diaphragm. Is essentially E times, what is E? What is E? E is elastance, which is essentially the inverse of compliance. Okay. Elastance times V of T. What is V of T? V of T is volume change, volume with respect to end expiratory pressure, okay, plus R times V dot of T. Note there is a dot here, V dot T. That what is V dot? V dot is time rate of change of flow, time rate of change of flow, plus the setting that you give an auto peep. This is the positive end expiratory pressure that you expect. If you want to simplify this a little bit, you can leave out some of these. Essentially this ventilator pressure is the sum of elastance times the volume change plus resistance times the flow rate. That is a simpler version of this equation. The other way to classify ventilators is to classify them based on the support they provide. Are they full support, partial, or assist, for example, right, or proportional assist, some form of proportional assist. Proportional assist. Then based on power transmission, what kind of power transmission is used? Based on limits, what is it that you are limiting? Are you limiting pressure, volume, or flow, for example, okay, or based on pressure patterns, okay, constant pressure, decelerating, or say for example sinusoidal. Based on the cycle control that you are using. These are the various ways in which you can classify the ventilators. Power transmission, for example, may be electric, may be pneumatic, or maybe hybrid. It might have electric control, but pneumatic actuation. That is the other possibility. Pneumatic actuation, electric control is another possibility. So, these are all the various ways in which you can classify, and each of this we have details on how this works. So, with this we come to the end of this introductory video on ventilators. In this video we introduced ventilator, the history and the types and some important terminology and the equation governing and various ways in which you could classify the ventilators. Thank you for your attention.